In Vsepr, we look at a Lewis dot structure and it gives us information about the shape of the molecule. Vsepr stands for valence shell electron pair repulsion. So a valence shell electrons actually tell us what shape it will go in. Why? Because the electrons repel each other. Now, one area of electron density is any of these, a single bond, a triple bond, a double bond, or a non-bonding pair. A non-bonding pair actually needs space to be in, and a triple bond needs the same space as a single bond because the electrons are in the same place between the atoms. So it doesn't need 3 places, just 1. So when we go to count the areas of electron density to find what the shape is, we are actually really looking to see the places where electrons are. So if we look at this molecule right here, this is acetylene, we can see that one carbon has 2 areas of electron density. So this is one area, a triple bond, and that's one area. That one area, those 2 areas, then want to stretch out and be at 180 degrees to each other, and we call the shape linear. If I look over here at this molecule, you will see that the carbon has 3 areas of electron density, as does the nitrogen have 3 areas of electron density. The 3 areas of electron density give this carbon a trigonal planar shape, and it gives this nitrogen a trigonal planar shape. And if I look at this entire molecule, all the atoms will be in one plane. Okay, and this non-bonding pair is stuck out in the plane of those atoms also. Down here, both the carbon with 4 bonds and the oxygen with 2 bonds and 2 non-bonding pairs have 4 areas, and they each are tetrahedral. So this is electron geometry. So what I want you to do now is look at the Lewis dot structures given here, and I want you to write down what would be the number of areas of electron density on each atom. And then on the next slide, what we're going to do is determine what is the shape for each of these. So pause and write down the number of areas of electron density for each atom. Okay, for this first molecule here, you can see that the oxygen has 1, 2, 3 areas of electron density. The carbon has 1, 2, 3 areas of electron density. And this nitrogen has 1, 2, 3, 4 areas of electron density. Over here, this carbon has 3, 1, 2, 3. This carbon has 3, 1, 2, 3. This oxygen has 1, 2, 3, 4 areas of electron density. So now the geometry of these comes about from counting those areas. So pause and determine what is the electron geometry of each of these atoms, and then start back up again and check your answers. Okay, for the first molecule, what you will see is that because oxygen has 3 areas of electron density, it will have a trigonal planar electron geometry. The carbon also, here we go, will have 3 areas of electron density, so it's trigonal planar. The nitrogen, however, though, is 1, 2, 3, 4, so it's tetrahedral. This carbon, trigonal planar. This one, trigonal planar. That one, tetrahedral. And that oxygen is tetrahedral. Okay, if you have non-bonding pairs, it's going to affect how we observe the molecule. Now, the electron geometry is the same. It's going to be what we have just learned, but the molecular shape is different from the electron geometry. Let's go down here and look at this molecule down here and see what we're talking about. If I look at the carbon, it has 3 areas of electron density, so it's in a trigonal planar shape. There is no non-bonding pairs on it, so the atoms are in a trigonal planar shape. But if I look at this nitrogen, it is trigonal planar with 3 areas of electron electron density, but at one point of that trigonal planar shape, you're going to have this non-bonding pair. Non-bonding pairs are not visible in the way that we normally look at the geometry of molecules. And so we will see, when we look at just the atoms here, we will see a bent shape for the carbon-nitrogen-hydrogen bond. Likewise, if we go over here, the carbon here is tetrahedral with no non-bonding pairs, so the molecular shape is tetrahedral. But the oxygen has 2 bonds and 2 non-bonding pairs, which is tetrahedral, but the non-bonding pairs cannot be seen, so the carbon-oxygen-hydrogen location of the atoms we say is bent. All right, so now what I want you to do is try these, look at these molecules, and identify what would be the molecular shape of each of these atoms. Pause and then check your answers. All right, if I look at each of these molecules, you can see that this carbon has 3 areas of electron density, which makes this electron geometry trigonal planar. It has no non-bonding pairs, and so its molecular geometry is trigonal planar. But the nitrogen has a non-bonding pair, so its molecular shape is not tetrahedral for the 4 areas of electron density. It is, the molecular shape is going to be trigonal pyramidal. If I look at this carbon, no non-bonding pairs, so both the electron geometry and the molecular shape is trigonal planar. But if I look at the oxygen, it's a tetrahedral electron geometry, but a bent molecular shape. Hybridization is another way that we explain bonding in the valence shell, and it is one of our more sophisticated ways of explaining bonding, and it seems to predict a lot of things correctly. So this model is a pretty good model. If we look at methane, which is carbon with 4 hydrogens on it, we find that we have 4 bonds attached, and the carbons are tetrahedral, and they're all identical. They are at 109.5 degree angle from each other. They all have the same bond strength, and they all have the same bond length. I cannot do that with these orbitals over here directly, because I have one orbital that's different from the other 3. And if I try to overlap these with some hydrogens, then what happens is you get one bond that's different from the other 3. So what do we do to explain this? What we do is we do it with something called a mathematical hybridization, where they take and mathematically cut these up into quarters and then recombine 1/4 of the s with 3/4 of the p orbitals. And when we do, we get an S4 sp3 orbitals. They're shaped like this down here. We are not concerned with the small end. It's too small to enter into bonding. We're concerned with the large end. And when we do this mathematical hybridization, we find molecular orbitals, or excuse me, atomic orbitals, that actually point at the corners of the tetrahedron. And so it predicts how bonding is going to occur very well. If I go and I look at a carbon that has these 4 sp3 orbitals on it, and I bring 4 hydrogen s orbitals, they can bond and make 4 equivalent bonds, which explains very well what we see in our test. Okay, so this is how we will, these are 3 different models of showing how we draw the carbon with the 4 equal carbon-hydrogen bonds. And if I look at this, they all have the same strength and the same length, and so it's explained well with 4 identical sp3 orbitals. Ethane, we can explain its bonding. Ethane is down here, 2 carbons surrounded by 6 hydrogens. if we hybridize each of those carbons, they can push together and we can get a sigma bond right here of an sp3 overlapping with an sp3, and then the hydrogens can come and sit down on each of these leftover sp3 orbitals and form 6 equivalent carbon-hydrogen bonds. Ethylene is a little more complicated. Let's hybridize a carbon sp2. That means you take one s orbital and 2 p orbitals to give 3 sp2 orbitals. You have a remaining p orbital that is perpendicular to the plane of those sp2 orbitals. Once you form this, let's say you have 2 of them, you can overlap those bonds, and we're going to look and see how you can form 2 different bonds between the carbons. So an sp2 hybridized carbon has 1, 2, 3 sp2 orbitals and this leftover p orbital. There's 1 electron in each of these 4 orbitals. If you turn it on its side, as is shown right here, the p orbital is sticking out of the page and the 3 sp2 orbitals are in the plane of the page. So this leftover p is perpendicular to the other orbitals. So now what I'm going to do is I'm going to have these 2 sp2 hybridized orbitals come in. So I'm going to bring this and this orbital together, and they're going to overlap and make a sigma bond. Then, when you have those overlap, these 2 p orbitals can overlap in a side-to-side fashion. And when they overlap in the side-to-side fashion, what do we get? We get a pi bond. A pi bond is where it's half above and half below the 2 atoms that are being bound together. And it's weaker, but it still strengthens the attachment between the 2 carbons. And it's above and below the 2 carbons at the same time. Half the bond is above, half the bond is below. And then you have these 4 sp2 hybrid orbitals that are left over, and that's where you'll have 1 hydrogen sit down on each of these sp2 orbitals. Here's acetylene. One of the carbons in acetylene is going to be sp hybridized. To make an sp hybrid orbital, you take 1 s and 1 p, leaving 2 p orbitals left over. This gives 2 sp hybrids, one of them here and one of them here. The 2 p orbitals that are left over, one is perpendicular to these 2, and then the other is perpendicular to the other 2 also. So an sp hybrid, an sp hybrid, 1 p orbital, and another p orbital. When they overlap, what we're going to do is this is really, the picture here is really hard to follow. But here is 1 carbon atom. Look right here. What do we see? 1 p orbital, another p orbital. Here is an sp hybrid, and here is an sp hybrid. Now what we're going to do is we're going to push them together. When we push them together, these 2 sp hybrids overlap and make a sigma bond. This and this, and the other half of it is down here and down here, they overlap to form a pi bond. This pink side and this pink side and that blue side and that blue side, they overlap and they form a pi bond. So what you end up with is there's an sp to a hydrogen sigma bond here, an sp to a hydrogen sigma bond here. And what do we have in here? We have a sigma bond that is formed by an sp to sp overlap, and then we have one of those extra bonds is a pi orbital, and then the other bond there is a pi orbital. So there are 2 pi orbitals with a sigma bond. All right, that was a lot of information, wasn't it? I got a summary for you that might help. And then another thing is try the problems in the book, and you're going to see the level of understanding here is not going to be super high. So if you do the problems and you start answering them correctly, you're going to start getting an understanding of what you need to know. Okay, to summarize Vsepr, if you have 2 areas of electron density, the bond angles are 180 degrees. You have a linear electron geometry, and you draw it just like this. What do you have? An sp hybridization with 2 leftover p's, giving 2 pi bonds. So every time you have linear arrangement, the atom that is linear must have sp hybridization and must have 2 pi bonds attached to it, either 2 pi bonds in one direction or 1 pi bond in one side and 1 pi bond on the other side. If you have 3 areas of electron density, you are always going to have 120 degree angles, and it will be a trigonal planar shape, and we draw it like this. This atom here must be sp2 hybridized with a leftover p on it. Either that p is going to be empty, as in the case of aluminum and boron, or it will be forming a pi bond with something. So you just have to look to figure out what it's forming a pi bond with. If you have 4 areas of electron density, the bond angles are 109.5. The electron geometry is tetrahedral, and we have a drawing that looks something like this. It's very hard to draw it this tiny, but we'll be doing some drawing on the board in class. This right here is always going to be sp hybridization. All the p's are used up. There's never a pi orbital. It's all sigma bonds. So now what I want you to do is go through, and on these structures I want you to identify which atoms are sp3 hybridized and identify which have tetrahedral electron geometry. Pause and then check your answers. Okay, any atom that has 4 areas of electron density, whether it's non-bonding pairs or bonding pairs, are sp3 hybridized and have tetrahedral geometry. So is anything up here with 4 bonds. So this carbon right here, you see it has 2 hydrogens, a carbon, and a carbon on it, so it's got 4 bonds on it. It's tetrahedral. That carbon has 3 hydrogens and a carbon on it, so it's tetrahedral. That nitrogen, a non-bonding pair, and 3 bonds. That oxygen, has 2 bonds and 2 non-bonding pairs, so it's tetrahedral. And so all of these that we have listed here, they're all tetrahedral electron geometry and sp3 hybridized. Now, go ahead and here, find those things that are tetrahedral, but are not having a tetrahedral molecular geometry. I want you to find those that have either bent or trigonal pyramidal molecular geometry. Okay, these atoms all have tetrahedral electron geometry, but because there's non-bonding pairs, they are not going to be tetrahedral molecular geometry. If there's 2 non-bonding pairs, it's bent. If there's 1 non-bonding pair, then it's trigonal pyramidal. Go through these molecules now and identify which are sp2 hybridized, which have trigonal planar geometry, electron geometry. Pause and then restart to check your answers. Okay. What we do to find sp3 hybridization, we look for 3 areas of electron density. So all the atoms that have 3 areas of electron density are identified here, and all of them have trigonal planar electron geometry. Now identify those that are sp hybridized and have linear geometry. The only ones here are going to be these 2 carbons because they're the only ones that have 2 areas of electron density.